Hi, the name of this Blender video tutorial is Constraint Controls. In it, we will look a bit closer at some of the common constraint controls, focusing on the transformation controls, space controls, and influence controls. To demonstrate these constraint controls, I've modeled in my Blender scene the basic drive chain components for a 19th century windmill. These are based on an existing grinding windmill located near Amsterdam. The most striking feature of any windmill is its rotating sails. These are connected to and transfer wind power to the wind shaft. Attached to the wind shaft is the main brake wheel gear. The sails, wind shaft, and brake gear assembly are set at a 15-degree angle rotated on its y-axis. The brake wheel gear transfers power to the wallower gear that is attached to the top of the main shaft, which in turn transfers power down through the windmill to a tail pinion gear. There are two double grinding gears on either side of the tail pinion gear, which in turn are connected to the vertical grinding shafts that turn the mill wheels. All the objects have their origin points centered on their geometry, and all the rotating objects have had their rotation setting applied, or Control A. I'll start the windmill constraint system by adding an empty object to the scene that will control the rotation movement. In side view, I'll place my 3D cursor to the right of the sails object and press Shift-A and add an empty object. I'll name this object Control Empty. I'll select the sails object, go to the constraint editor, and add a copy rotation constraint. In the target box, I'll select the Control Empty object. I want the sails to rotate about their local y-axis and respond to the Control Empty's y rotation. I'll uncheck the X and Z copy rotation checkboxes. In the space controls, I'll leave the target, which is the Control Empty, to be evaluated in world space, but I'll evaluate the owner, or the sails object, in local space. This means that the global y rotation of the Control Empty will be copied to the local y rotation of the sails, allowing them to maintain their original 13-degree angle. Now when I select the Control Empty and rotate it about its y-axis, the sails respond in kind, rotating about the object's local y-axis. I'll set the animation timeline to 100 frames. While in frame 1, I'll press the I key and insert a rotation keyframe for the Control Empty for frame number 1. I'll then go to frame 100. I'll set the Y rotation for the Control Empty to 360 degrees. I'll then add a rotation keyframe for the Control Empty on frame 100. I'll then go to the graph editor. I'll select the Control Empty y-axis animation curve and press the V key to make the curve a vector or straight line curve. I'll then go back to the 3D viewport and I'll play the animation. The Control Empty and the sails object rotate 360 degrees at a constant speed over 100 frames. I'll stop the timeline animation. I'll next select the wind shaft object, go to the constraint editor, and add a copy rotation constraint. In the target box, I'll select the Control Empty. Just like the sails constraint, I'll uncheck the X and Z copy rotation checkboxes, and I'll set the owner space evaluation, in this case the wind shaft space evaluation, to local. I'll select the brake wheel object and do the same. Add a copy rotation constraint, select the Control Empty as the target, uncheck the X and Z copy rotation boxes, and make the owner space local. Now when I play the animation, The angled sails, wind shaft, and brake object respond by rotating about their local y-axis. The next step is to transfer the local y rotation of the brake wheel gear to the global z rotation of the wallower gear. To complicate matters a bit, the wallower gear is 1/2 the diameter of the brake wheel gear, and it has 1/2 as many teeth, or in this case, pinion slots. Thus, the wallower gear should rotate twice the speed as the brake wheel gear. I'll select the wallower gear object, go to the constraint editor, and add a transformation constraint. In the target box, I'll select the brake wheel gear object. I want the wallower gear global Z rotation to take on the brake wheel's gear's local Y rotation. Therefore, I will select rotation for the source and rotation for the destination. In the source to destination mapping, I'll change the bottom setting so that we are mapping the source Y to the owner Z. That is, the Y rotation of the source, which is the target brake wheel, will be mapped to the Z rotation of the owner, which is the wallower wheel. In the space controls, the target, which is the brake wheel, should be evaluated in its local space, and the owner, the wallower, should be evaluated in its global or world space. The transformation controls provide 3 range sets for the source, the brake wheel, and 3 range sets for the destination, the wallower. 1 set each for the X, Y, and Z axes. We'll be working with the Y source ranges and the Z destination ranges. When using rotation, the source range is essentially asking the question, what range of rotation degrees from the source, in this case the brake wheel, should be evaluated? The destination range is essentially asking the question, what range of rotation degrees from the owner, in this case the wallower, should respond to the evaluated source range. To demonstrate, I will set the source Y range to a minimum of 0 degrees and a maximum of 180 degrees. I'll set the Z destination range from a minimum of 0 degrees to a maximum of 360 degrees. Now, if I manually move the animation timeline, the wallower rotates the full 360 degrees in the time it takes the brake wheel to rotate 180 degrees. Since this occurs in the first 50 frames, the wallower remains motionless for the last 50 frames, while the brake wheel completes its rotation. One would thus suspect that changing the source Y range to 0 to 360 degrees and leaving the destination Z range from 0 to 360 degrees would create a one-to-one relationship. However, as it is with much other functionality in Blender, things are not quite so simple. Now, as I manually move the animation timeline, the wallower rotates along with the brake wheel 180 degrees in the first 50 frames, but it does not rotate at all for the remaining 50 frames, while the brake wheel completes its full rotation. It appears that Blender evaluates the source rotation based on a negative 180 degrees to a positive 180 degrees. I'll change the source Y range from a minimum of a negative 180 degrees to a positive 180 degrees. Now, as I manually move the animation timeline, the wallower rotates along with the brake wheel 360 degrees in 100 frames. However, as noted earlier, we need the wallower to rotate twice the speed of the brake wheel, because it's 1/2 the size and contains 1/2 the number of teeth. Now, unfortunately, the constraint influence slider has a maximum of 1, so we cannot make the target rotation influence the owner rotation more than its full rotation. However, the transformation constraint allows us to increase the destination rotation by increasing the destination range. I'll set the Z rotation destination range to a minimum of 0 degrees and a maximum of 720 degrees, twice the source range in degrees. Now as I manually move the animation timeline, the wallower rotates twice the speed of the brake wheel, rotating 720 degrees in 100 frames. I'll play the animation. Now just as a side note, if we needed to rotate the wallower in the opposite direction, we could switch the Z destination range to a minimum of 720 degrees and a maximum of 0 degrees. This would cause it to rotate in the opposite direction. To transfer the rotation power to the main shaft, I'll select the shaft and add the wallower gear to the selection. I'll then press Ctrl P and make the wallower gear a parent of the main shaft. I'll then play the animation. The main shaft rotates at the same speed as the wallower. At the bottom of the main shaft is the tail pinion gear. I'll select the tail pinion gear object and add the main shaft to the selection. I'll then press Ctrl P and make the main shaft a parent of the tail pinion gear. I'll then play the animation. The tail pinion gear rotates at the same speed as the main shaft. The tail pinion gear is a bit smaller than the wallower gear, but since it is connected to the same main shaft, it rotates at the same speed, which is twice the speed of the sails. The double grinding gears on either side of the tail pinion gear are 4 times the diameter of the tail pinion gear and contain twice the number of teeth. I'll select the grinding gear number 1 object, go to the constraint editor, and add a copy rotation constraint. In the target box, I'll select the tail pinion gear. I'll uncheck the X and Y copy rotation checkboxes as I want to copy only the Z rotation. Both gears are evaluated in world space. I'll play the animation. As you can see, the grinding gear is moving too fast and it's rotating in the wrong direction. I'll set the influence slider for the copy rotation constraint to 0.25. And I'll check the Z invert checkbox, which will reverse the direction. I'll then play the animation. The grinding gear rotates 4 times slower than the tail pinion gear and rotates in the logical opposite direction. Because the tail gear has 1/2 the number of teeth, or in this case pinion slots, as the grinding gear teeth intersect every other tail pinion gear slot. I'll select grinding gear number 2, and I'll add the same copy rotation constraint. The target is the tail pinion gear. The copy rotation is in the Z-axis, inverted, and the influence is set to 0.25. I'll play the animation. Finally, I'll select each grinding shaft object and parent it to its grinding gear. I'll then select each mill wheel and parent it to its grinding shaft. I'll then play the animation. One final note on using the influence controller. I'll select one of the grinding wheel gears. Note that every 25 frames, the grinding wheel object repositions its X and Y axis. Now this effect is not noticeable because the gears are symmetrical. However, if there were an object protruding perpendicular to the gear, or the grinding shaft child, this jump in axis would be quite noticeable. It appears that the influence controller operates somewhat like the source range control on the transformation constraint. When set to 0.25, it uses the target's 0 to 90 degree rotation every 25 frames.